My name is Bohao Huang. I'm a PhD student in the Applied Machine Learning Lab at Duke. It's an honor for me to present our team's work today, solar array mapping in San Diego. Energy system information is a crucial component for the sustainability of the modern society. However, historically this information is difficult to acquire due to its limited availability. On the other hand, such information is often visible or can be inferred from the overhead imagery. For example, solar arrays can generate the energy. The poles and power lines distribute the energy, and the energy consumptions can be estimated by inferring the buildings and cars in an area. In this project, we propose to leverage the recent advances in deep learning combined with the abundant remote sensing imagery to retrieve the energy system information automatically. Specifically, we focus on mapping the solar arrays across the San Diego region in California. This means, as shown by the images on the right, we are interested in not only finding the solar arrays, but also predicting the size and shape of these arrays. To achieve this goal, we chose deep neural networks since they've been showing dominating performances in several applications recently. In our work, we choose a model named the U-Net. It is a series of trainable small filters organized in a specific way, which allows them to understand the input image and generate the desired output. This deep network relies on a module called encoder to grasp features from the input images. In our work, inspired by some recent studies, we switched these encoders to ones that are pre-trained on much larger datasets to yield further improvements. As many other machine learning algorithms, we have to annotate the data before training the models. We collected overhead imagery with a resolution of 0.3 meters in San Diego. To make it easier to process, we divided them into small tiles and randomly selected 16 urban tiles and 8 suburban tiles to annotate. This portion is intentionally maintained to make the selected tiles be representative of the overall imagery set. To evaluate the performance of our model, we use intersection over union to estimate how correct our predicted solar array masks are. As the name suggests, IOU measures the percentage of overlapping between the prediction and annotated masks. IOU is 1 when our prediction perfectly aligns with the ground truth, and 0 when there is no overlap. One last step to train the deep neural network with the dataset we created is the loss function. Loss functions are used to guide the filters change in a way that is more likely to generate our desired outputs. Cross-entropy is one type of loss function that is commonly used. It makes the predicted distribution of solar arrays similar to the ones annotated. However, it does not directly force the shape of the predicted solar arrays to align with the ground truth. In our work, we train our model not only on cross-entropy, but also with soft IOU, which is a differentiable approximate version of the IOU. Combining these two loss functions not only makes the training more stable and easier to converge, but also produces more accurate solar array masks. With the new loss function, we are now finally able to train and evaluate the model. Here we show some example images for qualitative comparison of our model with a baseline, which is a vanilla U-Net without all the modifications we just introduced. Not surprisingly, our model yielded an IOU of 0.67, which is significantly better than the baseline, which is 0.53. The RGB imagery, as the input of the neural network, is shown on the left. The predictions of the baseline and our model are shown on the second and third column, respectively. All green pixels are panels that are correctly predicted by the model. Blue pixels are panels that are missed by the model, and the red pixels are backgrounds that are predicted as panels by the model. Our model generally misses less panels compared with the baseline, and the predicted masks match the real panels better, which might be due to the usage of the soft IOU loss. Furthermore, here we show an application of our project where the solar arrays are detected by our algorithms automatically from the overhead imagery. At last, we conclude our work. To address the energy information retrieval problem, we implemented a deep neural network model with several modifications to automatically predict masks for the solar arrays. Results suggest our method yields substantial improvements from the baseline. Qualitative analysis suggests the predicted masks are generally in good quality. We hope in the future this method can be utilized in other regions or applications for energy system information retrieval. Thanks for listening. We're happy to answer your questions.